So here we have to discuss about superposition of two plane polarized light having perpendicular vibration. We have to discuss here superposition of two plane polarized light having perpendicular vibration. Let us consider a calcite crystal. Suppose this is a calcite crystal. This is calcite crystal having the principal section parallel to the surface. Suppose this is the principal section. Principal section is along the which is parallel to the surface. It is cut in such a way that it has the principal section along the surface. I can draw. So this is the principal section. The green. This is not a line. This is a section, right? Actually, this is something like you will. This is your calcite crystal. So it is in the form of cube. It is in the form of cube. It will go like this, right? It will go like this. So it is not a line, basically. It's a crystal, right? This is a calcite crystal. So these are the planes. These are your principal sections. Principal section will be in the form of a plane like this, right? The principal section is in the form of a plane like this. So it is like this. So these are the principal section, and suppose light is falling on this principal section just in front of it. Light is falling on this calcite crystal at this point. Suppose you have light falling over here. Light is falling along is perpendicular to. Suppose this is, if I call this axis as, say this is x-axis. Suppose I will draw a different color. Suppose I call it x-axis, and I call this as y-axis. Let's suppose, or a red color. So this is x-axis and this is y-axis, right? Say this is y. Then light beam is falling along z-axis. What I am saying is light beam is falling along z-axis. This is x, this is y. I am using left-hand coordinate system just for the sake of simplicity. So light is falling along z-axis. Light is propagating a plane polarized light. A plane polarized light is falling on this calcite crystal. This is a calcite crystal. This is calcite crystal. So light is falling along z-axis. Light is falling along z-axis. Z-axis can be something like this, right? Inward. Z-axis. I have drawn z-axis. Inward, right? So light is falling on the calcite crystal. I'll do it with z-axis. So light is falling along z-axis. Z-axis suppose inward. Light is falling on this calcite crystal, on this front face, and going into the crystal. Suppose the plane polarized light which is falling has the field vector. The rays have their field vector along this. This is the field vector. It makes an angle theta with the principal section. In that case, this E can be written as, I can write E as E naught. I can write E as E naught sine kz minus omega t. Right? It will be in E naught sine kz minus omega t. This plane polarized light will split into, when it falls on the calcite crystal, it will undergo a double refraction. It will undergo a double refraction. When it goes a double refraction, it will split into two waves. This one is called extraordinary wave. This will be extraordinary wave, right? The wave which is along the principal section. Wave which is vibrating, the light which vibrates along the principal section will be extraordinary wave, and the light which vibrates perpendicular to the principal section will be ordinary wave. This is extraordinary, and this is ordinary. So this is Ex, this is Ey. So light will fall on the calcite crystal. This light will break into extraordinary and ordinary. So it is Ex is extraordinary with all the vibration along the principal section, that is E naught cos theta sine kz minus omega t. They are propagating in z direction. And Ey, which is O wave, Ey is E naught sine theta. So this light is propagating along, this light is both the light are propagating in z direction, but the vibrations, the electric field lies along x-axis. That's called along x-axis, means along the principal section. So this is called E wave, and this is E wave, and this is O wave. So these light, when you have a plane Polarity light incident on the crystal, it will undergo a double refraction, forming the E wave and O wave. Now this E wave and O wave will travel through the whole crystal. Suppose the thickness of the crystal is T. It will travel through the whole crystal. Let me call E naught cos theta as say Ex, or say E1 sine kz minus omega t. E1 sine kz minus omega t. And Ey is E2 sine kz minus omega t, right? Now, when they travel through the whole crystal, then in that case, when they travel through the whole crystal, the optical path covered by extraordinary wave is mu et, and optical path covered by ordinary wave is mu ot. And now, since I have taken calcite, in case of calcite, mu O is higher than mu E. So when they travel through the whole crystal and emerge outside, they develop a path difference. This path difference is mu O minus mu E t. Mu O minus mu E t. So when they come out, they travel different path. When they come out, they travel a different path. So they will develop a phase difference. This phase difference is equal to 2 pi by lambda into delta x, that is 2 pi by lambda into mu O minus mu E t. So when they come out, your extraordinary wave will be E1 sine kz minus omega t, and ordinary wave will be E naught sine, the phase will be different. It will be delta. It will develop a phase difference of delta. They will develop a phase difference of delta. Alright. Now, in this case, see over here, when they will come out, now you have the two plane polarity light, with one having vibration along the principal section and other having vibration perpendicular principal section. So now when they come out, they will superimpose. This is E2, and after superposition, see what they are giving rise to: kz minus omega t plus delta. So this can be cos delta plus cos kz minus omega t sin delta, right? So this will be Ex upon E1 cos delta and 1 minus Ex square by E1 square sin delta, or Ey upon E2 minus Ex upon E1 cos delta whole square sin square delta. So on superposition, they will reduce to Ex and Ey will be following the equation. On superposition, you have the resultant wave for which Ex by E1 square, Ey by E2 square, and this is minus 2Ex Ey upon E1 E2 cos delta equals to sine square delta, is equal to sine square delta, right? So this is the relation which the resultant wave Ex and Ey component of the resultant wave are going to follow. This is the equation which the Ex and Ey component of the resultant wave are going to follow. Ex square upon E1 square plus Ey square upon E2 square minus 2Ex Ey E1 E2 cos delta equals to sine square delta, equals to sine square delta, and delta is the phase difference. Why phase difference is getting created? Because these two waves are experiencing different refractive index in the calcite crystal. Calcite crystal will present different refractive index to ordinary wave and extraordinary wave. This is extraordinary, this is ordinary. So due to difference in the refractive index, the optical part developed by them is different, and hence when they emerges out, they will develop a phase difference. Now let's take cases for different. Let's see what happens for different value of delta. I'll write this formula over here. This is Ex square E1 square Ey square E2 square minus 2 Ex Ey E1 E2 cos delta equals to sine square delta, right? Sine square delta. Now suppose delta is, suppose you have case 1 where delta is say 2 pi, 4 pi, 6 pi and so on. When it is so, the resultant wave will be having Ex Ey, which will be satisfying this equation, 2Ex Ey upon sine square delta, this is 0, that is 0, right? So it is Ex square upon E1 square plus Ey square upon E2 square minus 2Ex Ey E1 E2 equals to 0, or you can write it as Ex upon E1 Ey upon E2 whole square equal to 0, or it is pair of, you can see Ey is E2 upon E1, Ey is E2 upon E1 Ex, Ey is E2 upon E1 Ex, right? So the resultant wave will be having Ex, resultant wave will be having the X vibration, Y vibration, such that they will be following this relation, right? So it means they will be, after they come out, they will be vibrating like, you remember Lysa's figure, they will be vibrating in a way, let's see, they will be vibrating like this along the straight line passing through the origin, right? They are in phase, they are in phase, obviously they are in phase. So they will be vibrating, the resultant wave, the electric field will be vibrating along this direction, electric field will be vibrating along this direction, where this angle is tan inverse E2 by E1. And what is tan inverse E2 by E1? Where this angle phi, let's suppose, so phi is tan inverse, we can write this as tan inverse E2 by E1, tan inverse E2 by E1, so that's phi. And this also comes out to be, what was your E2 and E1? E2 was E sin theta and E1 was E naught cos theta, that is theta itself. Your phi is theta itself. So it means the field vectors, the resultant field vectors, or the field vector of the resultant wave is vibrating, making an angle theta with the principal section. Earlier also it was doing the same thing. It means the resultant wave is same as the instant wave. Whatever was the instant wave, the resultant wave is also same, and it should be, because when they splitted, they were in phase. When they are immersed, they are again in phase. So they will form the same light. So the light will remain plane polarized. Light is going to remain plane polarized with the field vibration making the same angle as the field vibration of incident light made with the principal section. Now, suppose your delta is, let's take the another case. Suppose delta is pi. Suppose delta comes to be pi, 3 pi, 5 pi, and so on. Or it can be minus pi, minus 3 pi, minus 5 pi, and so on. So in that case, let's see this case. Your Ex by E1 square plus Ey by E2 square plus 2Ex Ey equals to 0, right? So that is equal to Ex by E1 and Ey by E2 square is 0, or we can write Ey equals to E2 by E1 into Ex. Ey by E2 is E2 by E1 into Ex, right? So in that case, what will be the light? The emergent light will be having the field vector such that they are varying like this. So your resultant field vector is going to be, the resultant field vector will be vibrating such that the slope of this line will be vibrating along this blue line, right? This was the initial direction. Earlier, light was making an angle of theta. Now it's making an angle of pi minus theta. It's making an angle of pi minus theta. You can see it. This is tan inverse minus theta. So tan inverse. This is equal to minus tan inverse theta. That is, it's making an angle. The final resultant wave is moving. In the resultant wave has got all the field vibration along this direction. The incident wave was having all its vibration, making an angle theta with the principal section, and the emergent ray is also plane polarized. The emergent wave is also plane polarized, but it vibrates with a field vector making an angle of pi minus theta with the principal section. Earlier it was theta with the principal section. Earlier the electric field, the vibration was making an angle of theta with the principal section. Now it makes an angle of pi minus theta with the principal section. So this is the amount of rotation. The amount of rotation is pi minus 2 theta. It means when a plane polarized light is incident on the doubly refracting crystal like this, then in this case what is happening is it is converted into two, it is undergoing double refraction, giving rise to a extraordinary wave and ordinary wave. Now they are traveling through the whole crystal and undergoing a phase difference of pi, 3 pi and 5 pi. When they come out, they are superimposing, and on superposition they again form a plane polarized light, right? They again form a plane polarized light with vibration making an angle of pi minus theta with the principal section, where theta and pi minus theta is measured in the same direction. Such a crystal of such a thickness, we call it half wave plate. Crystal of such a thickness is called half wave plate. Crystal of the thickness which give rise to a phase difference of pi, 3 pi or 5 pi and so on is called half wave plate. 2 pi by lambda mod of mu naught minus mu e t. Why I have taken mod is because we don't know whether crystal is negative or positive. It can be positive crystal also. Here I have taken calcite, so it is negative crystal, but it can be positive crystal as well. So mu naught minus mu e t is giving rise to 2n minus 1 pi, or I can write mu o minus mu e t is n minus half lambda. This is n minus half lambda. and hence this is called half wave plate. It gives rise to a path difference of lambda by 2, 3 lambda by 2, and so on, right? So here this is called half wave plate. It means the action of half wave plate on plane polarized light is when a plane polarized light is falling on the half wave plate, it will immediately undergo a double refraction. Double refraction will give rise to E wave and O wave. These two waves will travel through the whole crystal and will develop a phase difference, and after they come out they will superimpose and will give you again a plane polarized light, but the vibration, the fields are making an angle of pi minus theta with the principal section. Earlier the plane polarized light was having field vibration making an angle theta with the principal section, and this theta is measured and pi minus theta are measured in the same direction. If this is theta in anti-clockwise, this is also in anti-clockwise direction. So earlier it was theta, now it is pi minus theta. So the amount of rotation is pi minus 2 theta, right? So the light remains plane polarized, but its direction of field vibration changes from theta to pi minus theta. All right. So that's called half wave plate, right? Now let's take another case. Suppose delta is say pi by 2. I'll take case 3 in fact. Suppose delta is pi by 2 or 3 pi by 2 and so on. Pi by 2, 3 pi by 2 and so on, right? In that case, what will happen is, in that case, the path difference will be such that it gives rise to, the path difference is such that it gives rise to a phase difference of pi by 2, 3 pi by 2 and so on. So path difference will be lambda by 4 in fact, right? So in that case, if you put delta equal to pi by 2, in that case it is Ex upon E1 whole square, Ey upon E2 whole square equals to 1. Ex upon E1 square plus Ey square upon E2 square is equal to 1. It's equal to 1, right? So in that case, what will happen? The light wave, the resultant wave is such that their components are undergoing this kind of variation. See, this is called circular, this is called elliptically polarized wave. In this case, see what will happen. I'll tell you. This is the tip of field vector. See, this is the tip of the field vector. It is moving in an ellipse. The tip of field vector, it will be such that the resultant wave will be such that the tip of field vector will be moving in an ellipse, right? The direction of field vibration won't be same. The angle which it makes with the principal section will keep on varying such that the field vector moves in this ellipse of the same major axis, E1 square, same as E2 square. So the field vectors are not moving in one direction. Field vectors, all the rays will have their field vector in one direction, but that direction won't remain constant. As the wave propagates, the direction of field vector will keep on varying such that the tip of the field vector is moving on the ellipse. That's called elliptically polarized light. That's called elliptically polarized light. That's called elliptically polarized light, right? So this is elliptically polarized light. Here a beam elliptically polarized, in the elliptically polarized light, the beams, the rays which forms the beam, they all are in one direction, but that direction does not remain fixed. That direction keeps on changing such that the tip of the field vector is varying, the tip of the field vector is moving on an ellipse. That's called elliptically polarized light. And if say this theta is pi by 4, in that case E1 and E2 will be equal, and in that case your Ex square plus Ey square is E1 square, and this is called circularly polarized light. In that case, the tip of field vector is moving in a circle. I can always see the elliptically polarized light as the two plane polarized light, with one having equation Kz minus omega t and Ey is is two plane polarized light with the phase difference of pi by 2, with the phase difference of pi by 2. So it can be E2 cos k z minus omega t. So you can always see the elliptically polarized light as combination of or the superposition of two plane polarized light with a phase difference of pi by 2, right? So the intensity will be, if you talk about intensity, it is E1 square plus E2 square, right? It is E0 square. The intensity doesn't change. See, intensity change only when you have certain losses of energy. You don't have any loss of energy involved over here. So intensity remain E0 square. Intensity does not change when the light is passing through this calcite. It only undergo double refraction, and after that it will superimpose and give you the light. So when the phase difference is pi by 2, 3 pi by 2, the final light which you get is elliptically polarized. If this theta is the angle which the electric field of the incident light made with the principal section. If this theta is pi by 4, then E1 and E2 will be equal, and the final light will become elliptically polarized light. I can see the elliptically polarized light as superposition of two plane polarized light having a phase difference of pi by 2, right? So when this is called, this particular the calcite crystal, the crystal of such a thickness which give rise to a phase difference of pi by 2, 3 pi by 2 and so on, is called quarter wave plate. So the action of quarter wave plate is, when a plane polarized light is falling on the quarter wave plate, it will undergo a double refraction. Now they will travel to the whole crystal, will develop a phase difference of pi by 2, 3 pi by 2. Then when they come out, they will superimpose and will generate the elliptically polarized light. In case of elliptically polarized light, all the rays forming a beam will vibrate in the same direction, but that direction does not remain fixed with time. It keeps on varying such that the tip of the field vector is moving on an ellipse. That's called elliptically polarized light. If this theta is the angle, this angle, the electric field which makes with the electric field makes an angle with the principal section, initial electric field of the incident light. If this theta is pi by 4, in that case your E1 and E2 will be equal, and that case is circularly polarized light. So this is how this is the action of half wave plate and quarter wave plate on a plane polarized light. That's very important. This is the action of half wave plate and quarter wave plate on the plane polarized light.